Welcome to this explainer. Today we're diving straight into the massive, hidden intelligence that carries the ultimate responsibility for safely routing modern high-speed trains. I mean, when you're dealing with hundreds of tons of metal just hurtling down the tracks, the margin for error is literally zero.
So, that brings us to a pretty high-stakes question. How exactly do these vastly complex rail networks prevent catastrophic collisions? Just imagine the sheer scale of it all. Without a centralized, lightning-fast digital brain making sense of thousands of moving parts, the entire system would just collapse into chaos.
Okay, let's dive into this. When we look at a stunning piece of modern engineering like the Vande Bharat train, it's so easy to focus on the speed and the aerodynamics, but the real hero here, it's completely invisible. It's the highly intricate, heavily redundant electronic interlocking systems operating silently in the background that actually prevent disasters. And today, we're exploring one of these exact systems, the MEDHA MEI633.
Here's our roadmap for the explainer. We'll start with the railway's digital brain, then look at the central interlocking unit, see object controllers in action, cover maintaining the MEI633 system, and wrap up with troubleshooting fault codes.
All right, Part 1, the railway's digital brain.
Think of the MEI633, kind of like a living organism. What's really interesting about this subsystem's ecosystem is how it visually maps the whole thing out. You've got the central interlocking unit right there in the middle, acting as the core intelligence, and from there, it connects to object controllers out in the field, panel processors for human commands, and data loggers that basically record every single heartbeat of the system. It can be installed as one centralized hub or distributed across a massive train yard.
Now here is a number that should absolutely blow your mind: 333 milliseconds. That is the cycle time of the MEI633. Literally every single third of a second, this system collects data from the entire yard, processes vital safety equations, and sends out fresh commands. It thinks at this incredible speed just to guarantee real-time safety.
Moving deeper, Part 2, the central interlocking unit.
To ground all this theory in physical reality, we're now looking at the actual central interlocking unit cabinet, the CIU. Behind these metal doors and blinking LED lights is where the absolute magic happens. Guys, this isn't just a computer. It's a fortress of redundant processors that are constantly, endlessly cross-checking each other.
So, what does it do? At its core, the CIU is the main computing subsystem. It really has one vital job: collecting yard information from the tracks and operator commands from the control room, and then running those vital interlocking equations. Basically, it acts as the ultimate judge. Even if a human operator makes a mistake and accidentally commands two trains to cross the exact same path, the CIU validates the math, realizes there's a danger, and point-blank refuses to execute that unsafe route.
Which brings us to Part 3, object controllers in action.
And this brilliantly illustrates how the system bridges the gap from pure digital logic over to the heavy physical track hardware. If the CIU is the brain, these object controller modules are the nervous system and the muscles. Situated much closer to the tracks, they take those safe commands generated by the CIU and turn them into physical actions, like literally switching a track point or changing a signal light from red to green.
Let's break down the anatomy of one of these object controller racks. It's incredibly modular. First up, you have the I/O COM cards, and these communicate back to the brain using ultra-fast optical fiber. Then you've got your input cards, called OCCIs, acting as those sensory nerves reading the physical status of the yard. On the flip side, the output cards, or OCOs, act as the muscles that physically drive the wayside hardware. And crucially, right in the mix, there's a vital cutoff card constantly monitoring health and voltage. It is always ready to just pull the plug if anything looks even slightly off.
All right, shifting gears to Part 4, maintaining the MEI633 system. Even the most advanced digital brain needs a good doctor to keep it healthy, right? Well, this is the maintenance terminal, and it's an absolutely indispensable tool for the signal engineers working behind the scenes. Instead of manually probing wires across miles and miles of track, an engineer can just look at this interface and get real-time visibility into the health of every single card, relay status, and fault code across the entire railway yard. It's a real game changer.
But the crucial point here is how the system handles the unexpected. The MEI633 is designed with rigorous self-preservation in mind. Its software refreshes the modules dynamically every cycle. Now, if the central CIU fails to refresh within 700 milliseconds, it forces a total safe system shutdown. But out in the field, the tolerance is even tighter. A field module timeout of just 350 milliseconds forces that specific track section into an immediate safe state. It fails fast, and more importantly, it fails safe.
And that leads us to our final section, Part 5, Troubleshooting Fault Codes.
The system is smart enough to distinguish between different levels of faults. Notice the difference we have here. An operational fault, like a point detection failed on point PT18, just means a mechanical track switch didn't lock properly. So the system logs it and halts that specific route. No big deal. But a critical safety failure, like an HR relay picking up unintentionally, that is highly dangerous. It's what they call a wrong side failure. The system instantly throws up a red alert and triggers vital safety actions across the board to prevent any trains from entering that zone.
So what happens when one of those printed circuit boards actually fails? Maintainers follow a very strict sequential procedure. First, they identify the specific fault code on that maintenance terminal we talked about earlier. Second, they attempt a hard reset by switching the specific card off and on using a physical push button. Now, if the system still registers a fault, they don't mess around trying to solder or hack it. They pull the faulty card out entirely and swap it for a fresh one. And if that still fails, well, then it's time to call in the specialized service engineer.
I want to share this direct quote straight from the source manual because it really anchors the whole concept for us. Failure to refresh with proper sequence forces the system to a safe state. This isn't just some dry technical specification, this is the fundamental philosophy of modern rail safety.
Ultimately, what this all means is that the MEI633's digital brain is programmed for absolute, uncompromising caution. It always prioritizes a safe failure over a dangerous operation. If it's ever confused, if a component breaks, or if it loses communication for even a fraction of a second, it stops everything. It ensures the railway never, ever acts blindly.
So, I'll leave you with this thought. The next time you're standing on a platform or just looking out the window of a train and you see that railway signal click over to green, ask yourself, what rapid, invisible digital conversations just successfully completed in the last 333 milliseconds to guarantee your safety? It's honestly an incredible piece of hidden technology. Thanks so much for joining me for this explainer. Keep wondering and keep learning.